All right. Welcome to this first example. We're going to be talking about our first introduction or journey into this idea of second order differential equations. And we're going to look at two specific cases. In this first case, we're calling them reducible. What that means is that we're going to take a second order and make a substitution and then be able to rewrite it as a first order differential equation. And so our first case, the case that we're going to look at and initially is when the dependent variable y is missing. So we have a function, a differential equation of the form capital F equal to, which is a function of x, y prime, and y double prime equal to zero. So it's a homogeneous differential equation, second order. And if it's of this form, meaning that it's missing any reference to a y dependency, then we can rewrite that with the substitution letting p equal y prime and y double prime being p, the derivative of p with respect to x or p prime. So that means that these two variables are going to be rewritten as p and p prime, and so we can transform it into a linear, first order differential equation from which then we can solve and then substitute back to find the general solution of that problem. So that's the scheme in this particular case. And so let's look at an example and see how that might look in practice. So here is our first example in this regard. So suppose we have x, y double prime. That's what makes it a second order differential equation. It's the largest derivative plus 2y prime equals 6x. Okay, so if this is our differential equation, you could imagine subtracting over the 6x, and then we have an x, a y prime, and a y double prime, but we do not have a variable y. Okay, all right, so if we make this substitution, then y double prime becomes dp dx, and y prime becomes p. So I can rewrite this differential equation in the form just making literally the direct observation. We have x dp dx plus 2p equals 6x. And then as in many problems, we may divide by everything by this leading function here to kind of put it in the more common form. And if I do that, I divide every term by x here, what I'm going to get is dp dx plus 2 over xp is equal to 6. So it's a constant term provided here that, of course, that x is not equal to 0. Okay. And if we look at this part right here, you should identify that this is, in fact, an integrating factor kind of problem. So our integrating factor is e to the integral p dx. That's a capital P. That's this 1 over x thing here. So this is 2 over x dx. Integrating that, you get e to the 2 natural log x. And then bringing that up, you get e to the natural log of x squared. The natural log and the e are inverses, reducing down to just an x squared term. So our integrating factor is x squared, which means this side collapses to x squared times p. We're going to take the derivative with respect to x there. And then on this side, of course, we get 6x squared multiplying through by the integrating factor. Okay, integrating both sides. This is pretty straightforward. This is just x squared times p is equal to adding 1 and dividing by that. Since the integral is with respect to x, this becomes x 6 over 3 from the from the x to the third power here. So this becomes 2x cubed plus a constant. Okay. And then, of course, we can divide everything through by x, and we get p is equal to 2 divided by x squared. This becomes 2x plus c, x to the negative 2. And remember now, p from our substitution was y prime, which allows us then to write dy dx is equal to 2x plus c e to the, not e, sorry, x to the negative 2. And this is then just a very nice integral. We can integrate both sides one more time with respect to x. And if we do that, we get y is equal to, this is going to be add 1 and divide. So this is going to become x squared plus add 1 and divide. That's going to be a negative 1, x to the negative 1 plus a constant. And I have a c there. So I'll have to call that maybe c1. and this is C2, and then rewriting it in just a little bit more of a compact form, if you will. I'm going to have x squared plus, I should just say, yeah, the minus can be absorbed into the C1. Just leave it as a plus C2, where C1 and C2 are arbitrary constants that would be determined by initial or boundary conditions. Okay. So this then is the solution to the second order differential equation. Again, with the substitution, it allows us to reduce it to a first order, and then resubbing and integrating one more time, we can get the second order solution. All right. I hope that was helpful, and I will see you in the next video.